Hello everyone, I'm Peihan. I'm excited to present our work, Compositional Neural Textures. This is a collaboration with Li Wei from Adobe Research and my advisor Matthias Wicker. Our research explores innovative ways to create and manipulate textures using compositional texture representation. To set the stage, let's talk about the importance of textures in computer graphics. Textures are fundamental in bringing digital objects to life, adding detail, realism, and aesthetic appeal. There are some related works on texture editing applications like interpolation, variation editing, weathering, style transfer, and edit propagation. Each relies on its own algorithm or specialized neural network. Our work aims to unify these approaches with a more versatile solution. Generative models like diffusion models and GAN have revolutionized content creation, producing highly realistic and diverse results. However, when applied to repetitive texture generation, they often lack precise control and can struggle with consistency. Our work builds on these advances, addressing this limitation to offer a more controlled and reliable approach to texture generation. GANs and diffusion models have been used to expand inputs to generate texture variations. While these approaches are impressive, they often lack explicit, human-intelligent representation, thus providing limited control over the generation process. Our work builds on these methods to provide a more general and adaptable framework. Before diving deeper into our method, it's important to first understand what are textures. At their core, textures are built from the basic element called taxons. Taxons are the microstructure found in natural images and videos and are considered the atoms of human visual perception. The foundational understanding guides our approach to texture generation. Let's look at some examples to understand what taxons are. In the first texture, which is highly regular, the taxons are clearly defined. For the second texture, there are more irregularities. The distinguishable elements still show us to define taxons. However, as we move to the third texture, which is more stochastic, the definition of taxons becomes less clear. Finally, in the fourth texture, which is with its high level of stochasticity, identifying taxons become even more ambiguous. So the key idea is to recognize the taxons that form the building blocks of a texture's appearance and model textures as taxon compositions. Through the modeling, we obtain a flexible, compositional neural representation for textures and gain control over texture generation at a fundamental level. Our goal is to train a single neural network with a compositional textural latent representation that can be applied to diverse applications. We demoed the applications in yellow boxes, and those in black boxes are left for future works. Once the network is trained, for different applications, we only need to modify the latent representation generated by the neural network. Getting the output only requires a forward pass of the input image to the neural network. Next, we introduce our neural network that decomposes textures into a composition of neural taxons. We obtain this compositional representation by developing a autoencoder architecture that is trained in a fully unsupervised manner. Each neural taxon is represented as a 2D Gaussian with an associated appearance feature. A Gaussian approximates a taxon's shape where its spatial parameters, and a Gaussian appearance feature encodes the taxon's exact appearance. Our compositional representation is capable of modeling a variety of textures. Training the neural network encounters a major challenge. Coming up with an exact definition of taxon is really hard. Can we use supervised approaches to find taxons, like semantic segmentation and human pose estimation? The answer is probably no, because we are unlikely to get consistently labeled texture dataset. Even if we have infinite resources for labeling image textures, the definition of taxons is ambiguous, and different people may have different opinions about how and which taxon should be labeled. So we train our network without data supervision. We hope neural net taxons to have a set of design properties for our user interactions, including discrete objectness. A taxon should either exist or non-exist, and there is no intermediate state. Spatial compactness. We assume the input image textures are repetitive. In other words, an input has many taxons instead of just a few. Reshuffling invariance, and this is actually the most important property. Given a set of neural taxons, if we randomly reshuffle their appearance feature among the set of Gaussians and reconstruct the texture from feature reshuffled taxons, we expect the output to be similar to the input in terms of texture similarity. Let me give an example. When we have a white paper texture, a taxon can either be a single pixel or a huge image region, because no matter how we reshuffle the appearance within these regions, it will still be a white paper texture. But if we have classboard, if we define taxon as a single pixel, then when we randomly shuffling the pixels, the chessboard texture will be destructed. And finally, transform equivariance, which is commonly used in many existing key-point object detection methods. When we apply transform T to neural taxons, we expect the reconstructed texture undergoes the same transformation, T, in the pixel space. This can help us to disentangle appearance and geometry. Here we briefly talk about the dataset and training. We use ChatGPT to generate 2,500 textual prompts, and we use Adobe text-to-image model for generating 400k images from these prompts. And we train a single model using 400k images. And here we choose some random samples from our generated dataset. In our neural network, there is a segmentation module which is responsible to segment input image into taxons regions, and here we show uncurated results on taxon segmentation. It shows our approach is able to segment reasonable taxons from a variety of textures. We also compare our taxon segmentation results with segment aliasing. And as expected, segment aliasing works better when taxon have semantic meaning, but it does not work when the textures are random, which are actually the majority of use cases. We can transfer appearance from one texture towards the geometry of another texture by using spatial Gaussians from one and appearance features from the other. We can transfer textures to a natural image by running the transfer algorithms on image patches, as the image patches can be viewed as repetitive textures. We can generate texture interpolations by interpolating spatial distributions of Gaussians and their appearance features. Texture morphing can be produced via a spatially varying interpolation. We can manipulate the variations within a texture by reducing or increasing the variations in appearance features and Gaussian covariances. Edit propagation can be performed by using the extractive structure of Gaussians. We can also directly manipulate taxons by moving, scaling, or rotating the Gaussians. We can also animate textures using flow fields. Our approach also poses some limitations. For example, the taxon we extracted lack semantic understanding of taxons. As we assume each taxon is locally compact, we can generate elongated taxons. And in the future, we plan to explore more applications using the compositional neural textual representation, and we also want to understand repetitions beyond those in digital images, such as videos, 3D models, audios, and materials, etc. Thank you.